At the outset, there existed an unimaginably dense mass of matter. This mass underwent an event that led to the formation of particles, stars, and galaxies as we observe them today. For many years, physicists have adhered to this explanation. However, recent research has introduced a new perspective suggesting that the universe may not have had the early beginning previously believed. Instead, it could be part of a cyclical process involving phases of expansion and contraction, possibly in a loop. Brian Cox, a prominent physicist, expresses skepticism regarding the Big Bang theory, arguing that something cannot emerge from nothing. This line of inquiry adds an intriguing dimension to the discussion. Furthermore, findings from the James Webb Space Telescope have presented evidence that challenges the notion that the Big Bang marked the definitive start of the universe. This raises a fundamental question. If the Big Bang was not the inception of the universe, then what was it? Join us on this journey to explore the origins of the universe, delving into the fringes of the Big Bang and seeking answers to this question. If you're passionate about staying updated with news related to the universe and its mysteries, consider subscribing to our channel, liking this video, sharing it with others, and turning on notifications. Scientists have developed a detailed understanding of the universe's early stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it is today, approximately 13.8 billion years ago. During that time, all the fundamental particles that comprise our existence formed within mere minutes. In this hypothesis, our universe, including stars and galaxies, was once as tiny as a peach and had an incredibly high temperature exceeding a quadrillion degrees. Interestingly, this astonishing narrative is continually evolving with new discoveries. Astronomers have examined everything from the remnants of electromagnetic radiation from the early universe to the formation of the lightest elements, finding that all evidence aligns with the predictions of the Big Bang theory as best as we know. Despite its compelling strength, we understand that the Big Bang theory does not encompass the entire picture. There remains an unresolved aspect of this mystery, particularly regarding the initial moments of the universe. This challenge is largely due to the limitations of our current theories. The combination of general relativity and high-energy particle physics provides us with a foundational theoretical framework. However, as we probe deeper into the universe's earliest moments, the mathematical complexity increases dramatically, leading us to a point where our existing models fail to yield significant solutions. One indication of this complexity is the presence of a singularity, an area of infinite density at the beginning of the Big Bang. This notion implies that the universe was once compressed into an infinitely small and dense state, which seems paradoxical. To tackle this challenge, we must explore new realms in physics and develop theories that can address these constraints and provide a more comprehensive understanding of the universe's origins. Our current instruments and theoretical frameworks are insufficient to confront this challenge, highlighting the need for new physics capable of integrating gravity with other fundamental forces at extraordinarily high energies. This is precisely where string theory becomes relevant. This theory aims to be a coherent model that unifies gravity with other fundamental forces, particularly at super-high energies. Essentially, string theory posits that it can elucidate the universe's early moments. Within string theory arises the concept of an aeon, derived from the Greek word meaning era or age. This idea suggests that the Big Bang, as we perceive it, was a result of a preceding event, implying that it was not an absolute beginning but rather part of a continuous cycle. The notion of an eonic universe has led to the development of a related theory known as cyclic cosmology. While the idea of a cyclic universe has been contemplated for centuries, string theory provides a robust foundation for this concept. In the framework of cyclic cosmology, the universe behaves as though it undergoes an eternal sequence of expansions and contractions, pushing the boundaries of our understanding, extending infinitely into both hypothetical the past models and future. Have been proposed to explore the nature of the early universe, each offering unique insights and perspectives. One such concept is the multiverse, which posits the existence of a vast array of universes, each with its own distinct physical properties and fundamental constants. In this framework, our universe is just one among many, arising from different initial conditions and governed by its own set of physical laws. The idea of a multiverse naturally emerges from certain interpretations of quantum mechanics and cosmological expansion theories. According to inflationary cosmology, The rapid expansion of spacetime in the early universe could have led to the formation of pocket universes within a broader multiversal landscape. Each pocket universe would exhibit its unique characteristics, shaped by random quantum fluctuations during the inflationary epoch. While the multiverse hypothesis remains speculative and difficult to test empirically, it offers an intriguing solution to the fine-tuning problem in cosmology, the puzzling observation that the fundamental constants of nature are perfectly calibrated to allow for the existence of complex structures like galaxies, stars, and life itself. Another compelling idea that challenges traditional notions of cosmic origins is that of eternal inflation, proposed within the framework of inflationary cosmology. Eternal inflation suggests that the universe undergoes an infinite series of inflationary phases, each giving rise to new regions of spacetime that may have distinct physical laws. In this scenario, our observable universe is merely one of countless regions within an ever-expanding cosmic foam. The concept of eternal inflation raises profound questions about the nature of time and causality within the multiverse. If inflationary bubbles continually spawn new universes, the idea of a singular beginning or ultimate origin becomes increasingly elusive. Instead, the universe appears as a dynamic, ever-evolving entity embedded within a larger tapestry of inflationary growth. Recently, advances in theoretical physics have sparked interest in alternative cosmological models that challenge the conventional narrative of cosmic origins. For instance, some scientists have explored the possibility of a cyclic universe, where the Big Bang is not a singular event but rather one phase in a perpetual cycle of expansion and contraction. In cyclic cosmology, the universe undergoes successive cycles of creation, evolution, and destruction, each culminating in a big crunch followed by another Big Bang. This cyclic universe theory draws inspiration from ancient cosmological ideas and modern theoretical frameworks like string theory. In string theory, fundamental particles are viewed not as point-like objects but as tiny vibrating strings of energy. The notion of a cyclic universe emerges naturally from certain formulations of this theory, suggesting that the universe may exist in higher-dimensional spacetime, where patterns of expansion and contraction result from the interactions of fundamental forces. While the cyclic universe hypothesis remains speculative and faces significant challenges in terms of observational evidence and theoretical consistency, it represents a fascinating attempt to reconcile quantum mechanics with general relativity on cosmological scales. By proposing a continuous cycle of cosmic renewal, cyclic cosmology offers a compelling vision of a universe without a definitive beginning or end, where each cycle builds upon the remnants of its predecessor. In addition to theoretical models, observational cosmology has provided crucial insights into the early universe and its evolution over cosmic time. The discovery of the cosmic microwave background (CMB) radiation in the 20th century offered strong evidence for the Big Bang theory, allowing scientists to visualize the universe as it existed just 380,000 years after its inception. Detailed measurements of the CMB by satellites such as the Planck Observatory have enabled researchers to map variations in temperature and density across the early universe with remarkable precision. Observational cosmology has also illuminated the large-scale structure of the universe, revealing the intricate web of galaxies, clusters, and cosmic filaments that span billions of light-years. By studying the distribution of galaxies and measuring their redshifts, cosmologists have traced the universe's evolutionary history, deducing its age, structure, and ultimate fate. One of the most intriguing discoveries in observational cosmology is the presence of dark energy, a mysterious form of energy that permeates the universe and drives its accelerated expansion. First inferred from observations of supernovae in the late 1990s, dark energy constitutes approximately 68% of the universe's total energy density, making it the dominant component of the cosmic energy budget. The existence of dark energy poses a significant challenge to our current understanding of fundamental physics, as its origin and nature remain poorly understood. Some theories suggest that dark energy may be an expression of vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's theory of general relativity to account for the observed acceleration of the universe. In response to these challenges, experimental physicists are actively searching for new particles and interactions that could shed light on the fundamental nature of dark energy. Additionally, other cosmic mysteries, such as those explored at the Large Hadron Collider (LHC) at CERN, aim to test the frontiers of particle physics by colliding protons at unprecedented energies, potentially revealing new physics beyond the standard model. Furthermore, advancements in astrophysical instrumentation have allowed scientists to probe the universe across various wavelengths of the electromagnetic spectrum, from radio waves to gamma rays. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have revolutionized our understanding of star formation, galaxy evolution, and the cosmic distribution of dark matter. Looking ahead, the next generation of observatories such as the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, promises to provide new insights into the early universe and its fundamental constituents. These cutting-edge instruments will enable researchers to study the first galaxies, probe the epoch of reionization, and search for signatures of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the origins of the universe represents one of the greatest intellectual challenges of our time. From ancient myths and philosophical inquiries to modern scientific theories and observational discoveries, humanity's exploration of cosmic beginnings has yielded profound insights into the nature of reality itself. As we continue to push the limits of knowledge and inquiry, new theoretical frameworks, observational techniques, and experimental advancements will undoubtedly illuminate the fundamental mysteries of existence and our place in the cosmos. Cyclic cosmology, proposed by the renowned physicist Roger Penrose, who was awarded the Nobel Prize, centers on a fascinating mathematical relationship between the early universe, characterized by extreme density and temperature during the Big Bang, and its future state, which is depicted as cold, expanded, and devoid of matter. This theory suggests that these two states become mathematically indistinguishable when pushed to their limits. Despite appearing paradoxical, the complete absence of matter might be the fundamental driver behind the creation of all the matter we observe today. According to this perspective, the Big Bang emerges from what remains, almost paradoxically, after all the matter in the universe has been consumed by black holes, which eventually scatter into dispersed photons in an immense void. The universe arises from a state that, from another angle, essentially resembles nothingness, though this nothingness still embodies a form of existence, an actual universe, albeit an empty one. The intrigue lies in how the same state can be interpreted as both a cold, empty universe and a dense one, depending on the viewpoint. The key to understanding this phenomenon lies in a complex mathematical technique known as conformal transformation, which alters the scale of an object while preserving its shape. Penrose demonstrated that the cold, empty state and the hot, dense state can be connected through this scaling transformation, despite their differences in size. He argues that under these extreme conditions, the concept of time loses its conventional significance. In cyclic cosmology, the sequence of events transitions from an ancient cold state to a young hot state, where the existence of the hot and dense state arises from the previous cold and void state. However, this causal relationship does not adhere to the traditional understanding of time, as both size and time lose their usual meanings in these extreme states. The cold, empty state and the hot, dense state exist on discrete planes, suggesting that, from the perspective of an observer within its own temporal context, the cold, empty state would persist indefinitely. Physics and theory are interwoven in this realm of cyclic cosmology, providing speculative yet detailed explanations for the beginnings of these cycles. Nevertheless, whether Penrose's ideas gain traction in cosmological developments, a deeper philosophical question remains about the origin of physical reality itself. How did these cycles come into existence? This prompts contemplation regarding the justification for the existence of something rather than nothing, which is one of the fundamental cosmic inquiries driving our exploration. Within the realm of physics, three potential scenarios arise when examining the origins of these cycles. First, there may be no compelling explanation at all. Second, there could be an infinite series of cycles, with each cycle representing a different universe, where the initial quantum state of each universe is somehow influenced by some aspect of its predecessor. Lastly, there's the possibility of a single cycle in a recurring universe, where the beginning of the cycle is explained by some element of its own end. These possibilities are intriguing as they avoid the need for uncaused events and offer a more intricate explanation within the framework of reality. Penrose suggests the concept of an unending series of cycles influenced by his interpretation of quantum mechanics. In quantum mechanics, A physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose proposes that each cycle is influenced by random quantum events, resulting in variations between cycles. This idea opens up promising avenues for testable physics, as it suggests the potential for identifying subtle traces or anomalies in the cosmic microwave background radiation from the Big Bang. The quest to understand the origins and nature of the universe has long been a central pursuit of human curiosity and scientific inquiry, spanning from ancient philosophical theories to modern cosmological models. Humanity has consistently sought to unravel the mysteries of existence itself. In the context of contemporary astronomy and cosmology, the exploration of cosmic origins has led to significant discoveries and captivating theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that has captivated both physicists and cosmologists alike is the nature of the universe before the Big Bang. While the theory of how the universe evolved from a hot, dense state to its current expansive structure provides a compelling explanation, it leaves open the question of what preceded this monumental event, if anything at all. The concept of pre-Big Bang time raises profound philosophical and scientific inquiries.